Have you ever been driving over a bridge and just wondered? I mean, really wondered how much incredible invisible work went into making sure it stays up. Well, today we're going to do just that. We are pulling back the curtain on civil engineering to see the whole meticulous process, from the very first survey of the land all the way to the final detailed blueprint.
I mean, that sounds like a massive challenge, right? You might think the answer is just, use more concrete and more steel. But it's actually so much more elegant than that. It all comes down to this incredibly rigorous step-by-step process that plans for every single possibility to guarantee total safety and a super long lifespan.
So, where do you even start with something this huge? Well, our journey today is going to break down into 5 key stages, and we are starting from the ground up, and I mean that quite literally. Okay, so before a single line is drawn on a blueprint, before any design software is even fired up, engineers basically become detectives. Their number one job is to get to know the environment intimately, the exact spot where this bridge is going to live for the next century or more.
And believe me, this data is absolutely everything. Hydraulic data? That tells them the highest the water could ever possibly get, like in a 100-year flood. The channel's width and depth? That sets the absolute minimum length the bridge has to span. And then they drill these boreholes deep into the ground to see exactly what they're building on. Is it solid bedrock, or is it something a lot softer? Every single decision they make from this point forward is built on this foundational knowledge.
All right, with all that crucial site data in hand, the engineers can finally start designing the main event, the part of the bridge we actually see and drive across. In engineering speak, this is called the superstructure. For this particular bridge, the design chosen is a reinforced concrete T Girder system. The easiest way to picture this is to think of a strong concrete road deck sitting on top of these massive T-shaped beams. And the key phrase here is cast-in-situ. All that means is that it's all built right there on location, poured as one solid, seamless piece of engineering. And it all begins with a 2D plan like this one. This is the master blueprint for all the load-bearing parts. It maps out every single dimension down to the millimeter, how far apart the girders are, the exact width of the road, everything. Now, from that 2D plan, things get really cool. Engineers create a 3D digital skeleton of the bridge inside some really powerful analysis software. It's called a grillage model. And it's not meant to look pretty or realistic. It's a simplified frame that lets them simulate with incredible precision how the bridge is going to bend and behave under all kinds of stress. So, now that this digital twin of the bridge is built, it's time to try and break it. The goal here is to subject that digital model to every single potential force it could possibly experience over its entire lifetime. This is where the virtual stress testing really kicks off.
Engineers really break it down into 2 main types of loads. First, you've got the dead loads. That's the constant, unchanging weight of the bridge itself, the concrete, the steel, the pavement. Then you have the live loads, and these are the dynamic, always changing forces from traffic, cars, trucks, you name it. And listen, we are not just talking about your average daily commute here. The design has to withstand very specific, standardized heavy loads that are laid out in the engineering codes. This means planning for absolute worst-case scenarios, like something called Class 70R loading, which simulates the immense weight of a military convoy, complete with tracked tanks. They even add an impact factor to account for the bouncing and vibrations of a moving vehicle. Okay, this is where it gets really, really clever. All those different forces, the dead loads, the live loads, the impact factors, they're now combined in hundreds of different ways to push that digital model to its absolute breaking point. The whole idea is to make sure it can pass the strictest safety codes with flying colors. This entire process is called the limit state design method. It's a modern way of thinking that checks the bridge against 2 critical thresholds. The first is the ultimate limit state that basically asks one simple question: will it collapse under extreme stress? The second is the serviceability limit state, which asks, okay, but will it perform well day to day without any weird bouncing or excessive cracking? So to pass the test, the design gets put through 3 critical checks. The flexure check makes sure it won't bend so much that it snaps. The shear check ensures it can resist forces that are trying to essentially slice right through the beams. And that serviceability check makes sure it's going to be comfortable and durable for the public for decades to come. Of course, a superstructure, no matter how strong, is only as good as what's holding it up. So now we have to go below ground, to the substructure. These are the critical parts that transfer all of that immense weight from the bridge safely down into the earth. And this is a perfect example of how that initial data collection drives the entire design. See, an open foundation would have been simpler and cheaper, but the data showed there was constant water flowing in the channel. That makes it impossible to dig a dry pit. So a pile foundation becomes the only real choice, driving these deep columns down through the water and soft soil to anchor the whole thing into the stable rock far, far below.
And get this, the foundation itself has to handle an incredible variety of forces. It's not just the crushing vertical weight of the bridge and all that traffic. It's also horizontal forces, like from a truck slamming on its brakes. It's subtle forces, from the concrete shrinking or expanding as the temperature changes. And yep, it's even potential seismic forces during an earthquake.
So here, we can see the final substructure design. You can see 6 individual piles arranged to work together as a single team. They're connected at the top by this thick concrete pile cap, which sits right under the end of the bridge. Its job is to evenly distribute all those different forces down into the piles deep below.
So in the end, you see that every single component is designed with this incredible level of detail. I mean, from the exact recipe for the concrete and the specific grade of steel rebar, all the way down to the tiny bearings that allow the bridge to expand and contract with the seasons. It's just an amazing reminder that our modern world is built on this hidden foundation of precise, invisible engineering. So what will you see differently next time you cross a bridge?